Hi, in this video we're going to look at one more theorem which is connected to one of the forms of Green's theorem. So let's look at the details here and then we will look at an example. So divergence theorem says if S is a closed, orientable, piecewise smooth surface. So for closed surface, we need the surface to enclose some kind of space inside of it. So like a sphere, for example, would be a closed surface, so that encloses a space inside that. A paraboloid without something on top would not be a closed surface. If I had a paraboloid and perhaps a plane forming the top of that, then I would have a closed surface. I need my surface to be orientable, so that means I need to be able to define an outer unit normal. So we looked at some examples before. We looked at the Möbius strip, which is a non-orientable surface, and we need our surface to be piecewise smooth. So the surface itself might not be smooth all the way around. If you think about this paraboloid that I've drawn here with a little plane on top, there is a sharp edge there where I would not be able to get a smooth parameterization or smooth XYZ equation that would define that edge. But I can split that into pieces where each piece would be a smooth surface. So a plane and a paraboloid, each piece would be a smooth surface. D is a region in R3 enclosed by the surface S. So we need a closed surface. D would be the region inside that surface. F is a vector field with continuous first partials on an open region containing S and D. So as with most of the theorems we've looked at in this chapter, we need continuous first partial derivatives of our vector field. And then there's a conclusion of divergence theorem, says that the flux of F through S, and in this flux integral you might notice that there is this circle. I haven't used that circle yet on a surface integral. That's just like for a line integral, when you see the circle there to indicate that you're interested in a closed curve. Similarly here, we need S to be closed. This theorem states that, so we wouldn't necessarily need to write that circle, but when you see that circle on a theorem, it's important that your surface is closed. So the left side of this equality in the conclusion of divergence theorem is flux of F across our surface S, that's a closed surface, is equal to, and then if you look at the right side here, that is the triple integral over the region D, so the region enclosed by the surface, of the divergence. So the total value of the divergence at all the points that are inside my surface S. And so this should look very close to the flux divergence form of Green's theorem. So for the flux divergence form of Green's theorem, we were looking at a two-dimensional curve and flux across a curve. And Green's theorem said that if all the conditions were met, that we could find that by looking at the total value of the divergence of F at all the points inside the curve, the R being inside the curve. And so the same idea here, we're just looking at a three-dimensional extension of Green's theorem, or you can think of Green's theorem as a two-dimensional reduction of divergence theorem. All right, so let's look at an example here. I need to find the flux of F through the surface of that sphere. So I do have a whole sphere, so that surface is closed. That's the big deal condition that you often have to check about whether you can use divergence theorem. Your surface needs to be closed. So I do have the entire sphere here, sphere of radius 2, centered at the origin. And I need to find the flux of F across the surface of that sphere. So I could evaluate the surface integral directly. I do not have any place where that surface has a one-to-one projection. So if I were going to integrate the flux integral directly, I would either need to split it into two surfaces, the top half and the bottom half, and do each part separately. Or I could use a parameterization of my surface using spherical coordinates and then do a surface integral that way. So I could evaluate the surface integral directly, the flux integral directly, but surface integrals are generally kind of a pain to evaluate. There's a lot of steps setting those up. And so if divergence theorem applies, often the triple integral is actually easier to do. So let's check all the conditions here. S is closed. It is orientable. I can define a unit normal vector to that surface. And it is not only piecewise smooth, it is completely smooth. So the entire surface is smooth. D is the region in R3 enclosed by the S. So D would be the region inside my sphere, all inside there. My vector field, F, is just nice polynomials here, and so that has continuous first partial derivatives everywhere. So all of my conditions for divergence theorem are met. So if I want to use divergence theorem, I can, instead of evaluating the flux integral directly, evaluate the total value of the divergence of F on the region enclosed by the surface. All right, so let's calculate that divergence. Remember that divergence is del dot F, so del x of the M plus del y of N, the J component function, plus del Z of P, the K component function. And so when I do that, I'll get 4 plus 0. So if I use divergence theorem on this problem, I get the triple integral over the region D of 8 dV. And so if I was going to set that integral up, it's important to remember that you're integrating not just across the surface, but over the entire region enclosed by the surface. So you might use spherical coordinates if you're going to set that up, since you have a sphere region. But you should also, at this point, recognize that that is just 8 times the volume of the region D. And D is a region that you know how to find the volume of. The volume of a sphere is 4/3 pi times the radius cubed. All right, so when I simplify that, I get 256 pi over 3. All right, so I have positive flux, which means that the net flow of the vector field across the surface of that sphere is outward in the direction of n. Remember that divergence also measures net flow outward from a point, so it should not be surprising to you that flux and divergence are connected. What perhaps is surprising here is that flux is measured across the boundary, our surface S, and we're looking at the total value of the divergence at all the points inside the surface. So that is perhaps surprising to think about that, but that's what divergence theorem tells us. If you look at the proof of divergence theorem, I think that's in our textbook, and there's some interesting connections to everything that's going on there, some limits and some things that you can look at with that. All right, that's it. So try some homework.